Here we go, the algebra of matrices. I really kind of think of it as the arithmetic of matrices. The goal is to add, subtract, scalar multiply, and multiply matrices. We have two kinds of multiplications, but no division. So, you know, how do you define operations on these objects we call matrices? Well, first you have to understand that remember what a matrix is. It's a rectangular array of numbers. It has an order. Every matrix has an order, right? The number of rows by number of columns. So we have to start with a definition before we define the operations. Two matrices, A and B, are equal or equivalent, i.e. A equals B, if and only if. IFF stands for if and only if. Their corresponding entries or elements are equal. So, I mean, this is a really basic definition. If you're told that the matrix 1, 2, 3, 4, so 2 by 2 matrix, equals the matrix with entries A, B for the first row, C, D for the second row, then you know for sure what A, B, C, and D are. A is 1, B is 2, C is 3, D is 4, right? There's a correspondence between the entries. You know, just in the last few hundred years, this notation has been invented. It's not that old. It's not like thousands of years old. And somebody had to invent, what's a way that makes sense to add matrices together? So we have three matrices here in this example. A is 1, 2, negative 3, 4. B is 0, negative 3, 2, 3. C is 0, negative 2, 5, 3, 7, negative 1. If you're inventing this, how would you add A and B together? What would be a way that makes sense? What's really the only way that makes sense? Add corresponding entries. And that's exactly what we're going to do. So it shouldn't be a big surprise. So A plus B, by the way, we use capital letters usually to represent matrices. Lowercase letters usually represent just single real numbers or a variable range of real numbers. So A plus B, now let me write this out since this is the first time we've defined it, is going to be 1 plus 0 for the upper left-hand entry, 2 plus negative 3 for the upper right-hand entry, negative 3 plus 2, lower left, and 4 plus 3, lower right. Now, would I expect you to show all that work? For this, no, just do it. You know, you could do it in your head. So what do we get for our final matrix? Just going across 1, negative 1, negative 1, 7. Whoops. It's a bad looking 7. Okay? So you define it. I mean, mathematicians aren't that crazy. They define it just the way you would expect them to. What if I asked you to find A plus C? What would you tell me if I asked you to find A plus C? So A is this matrix. C is this matrix. What would you tell me? No, you'd tell me to get lost. They're not the same order, so how do you add corresponding entries, right? So that's the only time it's okay to tell your teacher to get lost. Go blow your nose, Mr. Chamberlain. It's another way of saying get lost? I don't know. I just made that up. Okay, so what's the order of A? 2 by 2. What's the order of C? 2 by 3. So we say A plus C is undefined. I can think of a way to define it. Maybe you only add the corresponding entries in the first two columns or something. But in general, if you're not defining some new funky way to add it, we'll say that this addition is undefined since the orders or dimensions are different. Can't do it. Okay? Not too bad yet, right? And if I ask you to find 2A, what's a way that makes sense to do that? By the way, remember vectors? God, it's been a long semester. Doesn't it seem like vectors was like 6 months ago? Okay, remember vectors? Vectors are kind of like matrices. In fact, you could call them matrices, certain kinds, right? You could think of it as a row matrix, any vector, the way we've defined it in this class. So if you take 2 times A, think of how we multiplied a scale. This is called scalar multiplication, when you multiply a real number times a matrix. It was called scalar multiplication for vectors too, remember that? And it really did mean scaling the arrow if we thought of the vector as an arrow, right? So what do you think 2a, how is that going to be defined if it's going to be consistent with our vector version of scalar multiplication? You're going to multiply 2 times what? Every entry, right? Yep. So some things we do in math make sense. So what would this be, by the way? If a is 1, 2, negative 3, 4, just double everything. 2a is, help me out, it's Friday. I can't do arithmetic. 2, oh, you're going down. Oh, rebel. All right, I like that. 2, negative 6 going down. 4 and 8. Mathematical rebel, yeah. Okay. Now, take a look at what we're doing in part D. We're saying combine operations. Take b minus 2a. Okay. Are we going to do the subtraction first or multiply first and then subtract? Yeah, the order of operations is going to be the same for matrices as it is for real numbers. So we're going to take b minus 2a, but we have to take twice a first. Well, we already did that in part C, so we could just write it out like this. B is the matrix 0, negative 3, 2, 3. And we already know what twice a is. If we didn't know it, we'd have to compute it right now. So minus twice a is 2, going across 2, 4, negative 6, 8. And this gives us the opportunity to define subtraction of matrices, right? But subtraction is really just adding opposites. So what are we going to do here? Just subtract the entries in twice a from the entries in b, right? Yeah. So what's that going to look like? 0 minus 2. I'll go ahead and write it out since it's the first time we've looked at subtraction. What's the next one going to be if you write it out? Negative 3 minus 4. That's the upper right-hand entry once we simplify it. Then the lower left entry is, yeah, but I'm going to be a rebel and say 2 minus a negative 6. Or maybe you're the rebel for doing it all at once. I don't know. Defining mathematical rebels, I mean, come on. We're all kind of geeks, right? Us mathematicians, not you guys. 3 minus, actually, it's just 8, isn't it? 3, oh, you're, so you're not wrong. You were being a rebel. I like that. Next time I'm wrong, I'm going to say that. Yeah, I'm not wrong. I'm just rebelling. Okay. All right, and then what does that simplify to be? Going across, negative 2, negative 7, 8, negative 5. There you go. So no big deal so far, right? I mean, if I hadn't defined these things, you probably would have done the homework and figured everything out yourself, right? Just by trying what makes sense. Any questions on that? So in this one example, we defined addition, scalar multiplication, subtraction, how to combine operations. So this is the mathematics appreciation portion of the lecture. What is an algebraist study? Probably algebra, right? An algebraist? Yeah, probably algebra. And if you think about, did it ever irritate you? It irritated me when I first learned about algebra. I think I started learning, I had pre-algebra in 7th grade, I think. That's what they called it. And they named all these laws, there were all these definitions, it was just irritating. But this is what algebraists study. These laws of addition, in this case, correspond with laws of addition for real numbers, which is what I studied in pre-algebra, right? And they had all these names for these laws. It didn't seem that important to me, but that's all that algebraists care about. They care about these laws, which really describes relationships between quantities. The quantities themselves don't matter that much, whether they're numbers or matrices or something else. And the crazy thing is the laws of algebra that you'll get in a course called abstract algebra. That's a more advanced course, upper division. It's not like the algebra we do in here. There's something called group theory and ring theory and all kinds of stuff. The crazy thing is it has applications in quantum physics. And quantum physics is, you know, it's not new, but it's a very important frontier in physics. Nanotechnology is huge, and you're going to be hearing more and more about that in the coming years. And quantum physics is integral to understanding and developing nanotechnology. Anyway, the commutative law. The commutative law, well, if you commute to work, you move, right? So if you want to take A plus B, think real numbers. It works the same for real numbers. You could move those guys around. Instead of A plus B, you could rewrite it as what? B plus A. So 5 plus 3 is equal to 3 plus 5. Those are real numbers. Works the same way for matrices. A plus B is equal to B plus A. Now, that should be fairly intuitive, because how do we add matrices? Corresponding entries, right? And we're just doing regular real number addition on those corresponding entries. There's no reason why you can't turn each one around, which means there's no reason why you can't turn the entire matrix addition around. Associativity, okay, say you have 3 matrices, A, B, and C, and you're adding them together. Have you ever noticed you can only add, if you're talking numbers, you can only add 2 numbers at a time, right? Even if you have 3 or 4 or 5 numbers, you add 2 at a time, don't you? It's called a binary operation because you add 2 at a time. Well, what associativity tells us is you could take the B plus the C, so get an actual matrix for this, a single matrix, right? And then add A to whatever that is. And you guys are familiar with the parentheses. Oh yeah, do B plus C first, add A. Well, associativity tells us that doesn't matter. I mean, you could add A and B first, so put that in parentheses, and then add C, and you get the same thing. So it works for real number addition. There's no reason why it wouldn't work for matrix addition, because matrix addition depends on real number addition. Okay, additive inverse. Let's go back to real numbers. What is the additive inverse for like the number 6? Yeah, it's the number you would add to 6 so that when you add them together, you get 0, which is the additive identity, right? So this is the additive inverse, real number-wise, and 0 is actually the additive identity, real number-wise, right? So in general, if you have a number x, just take the opposite of x to get the additive inverse, right? Well, it's going to work in a similar way for matrices. So if you took, say, A plus, what would we mean by the opposite of A? You'd multiply -1. Did you hear what he said? What he said, what do we mean by the opposite of A? And he said negative A. Well, yeah, we mean -1 times A, right? I know that's what you meant, but it sounded funny. It means -1 times A, right? So in other words, if you take the opposite of every entry in A, then every individual entry is the additive real number inverse of the corresponding entries in the matrix, the original matrix A. So that when you add them together, you get what I would call the 0 matrix. Now, we're going to call that 0, but you have to keep in mind that it's not the number 0. It's the 0 matrix, so I'll write matrix in a subscript. So A has a particular order, right? Number of rows by columns. That 0 matrix is going to have zeros and have in every entry, in the same number of rows and columns that A has. Okay? So if A is the matrix 1, 2, 3, 4, then first of all, what's the additive inverse? Let's start with that. Additive inverse. It would be negative all those numbers. Okay, I like that. Keeping it short. And then when you add those together, you get this matrix of the same size, same dimension, but all 0 entries. So this is the guy we're calling the 0 matrix. Does that make sense? So negative A is the additive inverse. And then the additive identity, we've already defined. You take A plus its additive inverse, and you get the additive identity. In other words, if you take A and add 0 to it, then we get A back again. That's why we call it the additive identity. Does that make sense? So the matrix full of zeros, which is the same dimension as A, is the additive ID. Does that make sense? It works the same way with the number 0 for real numbers, right? If you take x plus 0, you get x back again. 0 is the additive identity. So again, I mean, these properties don't seem that important here, but later on, if you go on in math, they become very important. A couple more laws. Scalar multiplication works just the way you think it would. So you have to understand what I'm trying to denote here. The distributive law for scalar multiplications, there's two ways to think of it. Lowercase letters represent real numbers. So I'm saying if you take a real number b and add it to a real number c, and you multiply that times a, you can essentially distribute the a, is what's going to happen. So if you distributed the a to both of these real numbers, what would you get? It would look just like the regular distributive law you're used to. B times a, right? Plus little c times a. If you don't believe that, make up a matrix like I just did, 1, 2, 3, 4, and make up a couple of real numbers, and you'll see very quickly, work it out for both sides of that equation. You'll see very quickly that is true. And then what if you take a single scalar times a sum of two matrices? What's your prediction for what that'll equal? So c times quantity a plus b is equal to c times a plus c times b. Again, it takes a little more thought than the other addition properties, but we're not going to take time in class to prove this. If you want to play with this property, if you want to be an algebraist, go for it. Make up a couple of matrices and prove to yourself that that's true. The associative property, if you have a scalar and another scalar, but you first take that scalar and scalar multiply it times the matrix, and then multiply on the left by a. So b times a is a matrix, right? Scalar multiplication. And then you do another scalar multiplication, a times b, that matrix, b times a. What is that going to be the same as? And again, we're calling this the associative law. So what do you think we're going to do? What do you think we're going to move around based on your experience with the associative law in the past? Yeah. So we're going to say that a times the matrix, b times a, is the same. You'll get the same thing if you do the scalar, multiply the two scalars first, a times b, and then multiply that scalar, whatever that is, that product times a. So the next big idea is matrix multiplication. Now this is important, and you're going to see an example today that actually will make it seem more relevant to your everyday life, especially if you're going to be any kind of researcher. Because matrices are a great way to organize and manipulate data. But before we do any of that, I have to describe to you how we actually multiply two matrices together. So this is the second kind of multiplication that we talked about. Let's start with multiplying what I would call a row matrix. So do you guys see why we call this a row matrix? What's the order of A? A is the matrix 2, 3, 4 going across. What's the order of this thing? Okay, number of rows by columns. I see one row, right, going across by how many columns? There's 3 columns, each with a single number in it, right? 3 columns, each with a single number. So we would call this a 1 by 3 matrix. So since it has a single row, we call it a row matrix. On the other hand, B has how many rows? No, you remember rows run across, so I would think of 7 as a row with a single entry. It's its own row. 6 is a row with its own entry. -5 is a row with its own entry. So there's actually 3 rows, but then there's just one single column. Does everybody see that? Okay. So we call that a column matrix. So this would be a 3 by 1 matrix. And this is how we create all matrix multiplication. We reduce it to a row times a column. So we're going to take A, the vector 2, 3, 4, times B, the matrix going down, 7, 6, -5. So usually what we do is we write it out, 2, 3, 4, there's your matrix A, 7, 6, negative 5. And the way we define this is a row matrix times a column matrix. The way it's defined is there's a kind of correspondence, even though those matrices are different orders, there's a kind of correspondence, right? So going across in the first matrix, you have the first entry 2, the second entry 3, the third entry 4. In the first matrix. In the second matrix, you go down, the first entry is 7, the second entry is 6, the third entry is negative 5. So we just multiply first entry times first entry, second entry times second entry, third entry times third entry, and we add together. So multiply corresponding entries, and what do you get? So this is the work. Now this is the work I will require you to show, because it's really important you know how to do this by hand, so you know how to interpret when you use matrix multiplication to manipulate data. You have to know what is going on by hand, even though you're going to do it by machine, so you can interpret what the output represents. Does that make any sense? You'll see what I mean in just a little bit, if that didn't make sense. So multiply corresponding entry. So you don't have to show me 2 times 7, but you would have to show me the 14. So this first step you don't need to show me. 2 times 7 plus what's the next one? If we write everything out, since it's the first example. So 2 times first entry, add that to second entry times second entry, 3 times 6, add that to what? There you go, third entry times third entry. And then, so this is the step you need to show me, the actual product individually. 14 plus what? 18 plus negative 20, so minus 20. I would need to see this. Otherwise, I don't know if you're doing it on the calculator or not. Not that anybody in here would possibly do that, right? Actually, I recommend, if you don't know what to do, I recommend you do that. At least you'll get partial credit, right? But you do need to show, if you want full credit, you need to show me that step. Okay, anyway, what do those add together to be? I think it's going to be 12, isn't it? Yeah. So in your mind, the easy way to do that is to go the 18 minus 20 first, negative 2, right? Plus 14. Okay? Now let's analyze a couple of things here. The reason why there was that correspondence in the first place that we talked about, between first entries, second entries, third entries, is due to the order. This was a 1 by 3, and A was a 1 by 3, and B was a 3 by 1. So in order for there to be that correspondence, if you have a row matrix and a column matrix, in order for you to have a correspondence, you have to have 3 columns in the first matrix on the left, A, or the same number of columns in A, the first matrix, assuming A is the first matrix, as rows in B. And so it doesn't matter if it's 3, it could be any number, but as long as they match up and are the same. So the number of columns in A, your row matrix, has to match up with the number of rows in B, your column matrix. That's confusing. So just remember that the inner numbers, when you write down the orders, the inner numbers have to match up. And you have to write down the orders in the order that you're multiplying, because multiplication of matrices does not commute. You can't turn it around like you can with real numbers. And that's the reason for the correspondence. If this had been a different number, for instance, then you wouldn't have a first times a first. Well, you could have a first times a first and a second times a second and perhaps a third times a third. But if this had been 4, there would have been another entry down here. And there wouldn't be anything to multiply it by over here. So not all multiplication of matrices is defined. So now we have 2 matrices that aren't either a row or a column. So we have matrix A, 1, negative 2, 3, matrix, and then 4, 0, 5. And then matrix B, 2, negative 1, negative 3, 1, and 0, 4. And we're asked to find A times B. So I'm going to write these matrices right next to each other. It's nice to kind of line them up right next to each other when you do the multiplication. And let's first analyze the units, though. The dimensions, rather. What would the dimensions of A be? The order of A, same thing. 2 by 3. And what's the order of B? 3 by 2. Do the inner numbers match up? So the multiplication is going to be possible, and here's how you do it. I think I'm going to give you a spoiler, just because it does make it easier. The outer numbers give you the order of the resulting product. So we can expect a 2 by 2 matrix as our product, okay? Outer numbers are both 2. Okay, so what's the process? Well, you're going to take rows times columns. So to get the first row, rows times columns, I should say. To get the first row of entries, which is just going to have 2 entries in it because it's going to be a 2 by 2 matrix, you're going to take okay, so let me start with the upper left-hand entry. You're going to take the first row in the left-hand matrix A and multiply it times the first column in the right-hand matrix, which is matrix B. In other words, this is going to look, to get the upper left-hand entry in the product matrix, it's going to look like that example we just did above. We're going to take row times column in the same way we just did above. So let's write out what we would get if we take row times column. So, okay, let's take the 1 times the 2. So that's 2. I'm going to write it out for now, and then to show your work later on, you're just going to write down 2, not 1 times 2. But because it's the first example of 2 non-row or column matrices multiplied together, I want to show that. So 1 times 2, and then what's the next one? You're going to add in -2 times -3. Would you buy that? As long as it's cheap? Okay. And then what's the next one? 3 times 0. And again, normally you would just say 0 like you just did. But since it's the first example, I'm showing it. I might not show it for the rest of the entries, but I wanted to show it for at least one of them. That's the upper left-hand entry. We know it's a 2 by 2 matrix, right? So there's one more upper right-hand entry. So how do you get it? Well, I'll show you. You go on, you keep the first row in A circled. You're going to multiply that row times the next column over in B. Whoops, I erased too much. So you're going to circle the next column over in the second matrix, but you're going to keep this row circled and multiply first row in the first matrix times second column in the second matrix to get the next entry in the first row of the product. Whew, that's a mouthful. So what do you get when you take row times column? What's 1 times -1? -1. -2 times this one right here. What's that? So plus a -2 or just -2? And then what's the next one going to be? Plus 12. Does everybody see where these numbers are coming from? Once you get it, it's not hard. Until you get it, it seems weird. It seems confusing until you really grasp it. Now, I didn't show all the individual multiplications. I just did them. Does that make sense? Okay, that's the upper right-hand entry. We'll simplify that in the next part of the problem. Now, to get the lower left-hand entry, you're going to start over, but with the second row in the first matrix circled. So you're going to circle the 4, 0, 5, and then you're going to get the second row in the product by doing the same process, only you're going to multiply the second row in A times, eventually both columns in B. So to get the lower left-hand element or entry, you're going to multiply the second row in A times the first column in B. So what do you get individually? What do you get? 4 times 2? 8. Everybody see where that's coming from? 4. This 4 right here times this 2. What's the next one? Plus 0 times -3 is 0. Plus 5 times 0 is 0. Now, I do want to see that work. When I ask you to show your work, this is what I mean. You don't need to show as much work as I showed in the first entry, highlighted kind of in purple there, but you do need to show the work in the second entry in the first row and that sort of work with the plus 8 plus 0 0 8 plus 0 plus 0 rather in the lower left hand entry. I do want to see that to make sure you know how to do this by hand, because calculators will do this, obviously. But it's still super important you understand what the calculator's doing so that you know how to manipulate data, especially if you're going to get into any kind of research. Okay, so now the lower right-hand entry is going to be obtained by, okay, you stick with the second row in A, but now you shift over to the second column in B. And what entries do you get there? 4 times -1, -4, what's the next one? 0 times 1, and then 5 times 4, so add that in, 20. Let's clean this up, and then we'll have our answer. What do we end up getting for the upper left-hand entry? So, yeah, it's 2 plus 6, because we have 0 on the third term. So 8, and then what do we get over here? 9, and then 8 and 16. There you go. There's your product. So the note then is, let's say you multiply matrix A, which has order m by n. So m rows, m is a counting number, n is a counting number, m rows by n columns. And B has order n by p, n and p are counting numbers, n rows and p columns. Notice that for the multiplication to be possible, these inner numbers have to match up. So you have the same number of corresponding entries so that you can take rows and times columns, right? And then the order of the product will be given by the outer numbers. So A times B as a product will have order m by p. If the inner numbers don't match up in the first place, just say the multiplication's undefined. Don't even try to do it. So we have matrix A with entries 1, -2, 0, -3. Matrix B, 3, 0, 4, -1, 5, 0. Find B times A. Let's analyze the orders. What's the order of B? Excuse me, what's the order of A? 2 by 2. What's the order of B? 2 by 3. So can we do B times A? So B, let's just analyze it right here. B, you told me, is 2 by 3. A is 2 by 2. What are you going to tell me when I say multiply B times A? Get lost. You can't do it, right? So undefined. We're going to look at whether or not we can do A times B. So now if we analyze the orders, A, like we said, is 2 by 2. B is 2 by 3. So that's supposed to be a 2 right there. Can you do it? The inner numbers match up. The number of columns in A matches up with the number of rows in B. That's what has to happen. So this is defined. So by the way, what does that tell you right away? Okay, every time you multiply real numbers A and B, doesn't matter if you take A times B or B times A, right? If these are real numbers. That's called the commutative property or commutative law of multiplication of real numbers. Is there a commutative a law of multiplication for matrices? No, it's not true. One of them's not even defined. The B times A isn't even defined. So some of the laws of algebra from real numbers hold, as we've seen. Some of them don't. This one doesn't. All right, you guys want to try this one on your own? See if you're awake? Try this one in your notes. Remember, to get any particular entry, you take row times column. What would the upper left-hand entry be? Give me the work that I showed in the last example. So just 3 would be plus or minus 2? Plus 2. That's the upper left-hand entry, 5, right? Okay. So what would the middle entry be? So yeah, this guy times this guy, 0 minus 10, I think I heard. Is that what I heard? Yeah. Okay. Everybody see where that's coming from? Okay, what would the third entry in the first row be? 4 plus 0. That's the work you're going to have to show for the first row. You have to show it to get credit. And it's going to be on the final. Okay? No questions on that? Okay. What about the lower row? Oh, by the way, how did I know there were going to be 3 entries in the first row? Because if you look at the outer numbers, it's 2 by 3, so there's 3 columns, so 3 entries in the row. The number of columns gives you the entries in the rows, right? Okay, so now in your notes, hopefully you went down to the second row in the first matrix and then start over with the columns in the second matrix to get the entries in the product. So what do you get there? 0 plus 3. Okay, I buy that. And then what? 0 minus 15. All right. And then 0 plus 0. Okay, so finally, what? 5, negative 10, 4, 3, negative 15, and 0. Note, there is a multiplicative identity for an n by n matrix. N by n, we would call that a square matrix because it would have the same number of rows as columns, n rows by n columns. If it's a, we'll call it I for identity. If it's a 2 by 2 matrix, then it's the multiplicative identity is the matrix with zeros off the main diagonal from upper left to lower right and ones down the diagonal. And then if it's 3 by 3, you're going to have a diagonal with 3 entries and zeros off that main diagonal of ones. And then in general, if it's n by n, you know, you just keep going. I don't know what n is, but if it's n by n, you just keep going down 1, 1, 1 in that stair-step pattern until you get n of them. And then you're going to have zeros off, you know, off the main diagonal. And how many of them will be there, I don't know, so I'll just use a big 0. So ones down the main diagonal, zeros elsewhere. That's the multiplicative identity. Do you believe it? Let's try it. Let's take 1, 0, 0, 1. And let's just multiply it times a different matrix and see if we get the same matrix back again. So give me a matrix. Don't get too creative. 3, 2, 1, 2. Okay. So let's do the multiplication. We should be able to do it, right? Any square matrices, the inner numbers will match up. The number of columns in the first matrix will match up with the number of rows in the second matrix. So what happens when you multiply 1, 0, the row 1, 0, times the column 3, 1? That'll give you your upper left-hand entry. What will that give you? 3 plus 0, right? 0 times 1. Okay, let's go over here to get the second entry in the first row in the product. 1 times 2 is 2, plus 0 times 2 is 0. And you can see it happening, right? So you get 3 and 2, just like you're supposed to. And then to get the bottom row in the product, go to the bottom row of the first matrix and start over with the columns. 0 times 3, 1 times 1, will get you the 1. And then go to the next column, 0 times 2, plus 1 times 2. And you do get the matrix 3, 2, 1, 2, just like we wanted to get. So that at least if you multiply on the left, we didn't prove it if you multiplied on the right, but at least if you multiply on the left, you take the matrix 1, 0, 0, 1 times another 2 by 2 matrix, and you get that 2 by 2 matrix back again. That's the identity. That's what the identity does. Okay, now you may not be a sports fan, and that's fine. What I want you to concentrate on here is how we're using the matrices to organize data, to organize information, and also matrix operations to make statistical analysis easy. Because you could translate this to anything with data, not just sports. So here we go. Matrices F and S give the points scored, number of rebounds, and minutes played for the starting 5 in a 2-game basketball tournament. So we have our first matrix here. I'm not going to read off all this for you. Points, columns would represent points scored. First column, second column rebounds, third column minutes, and then starting 5 corresponding to rows. So Hurd in the first game scored 21 points, had 5 rebounds, and played for 35 minutes. Okay, yeah, just to make sure you're reading it correctly, how many rebounds did Dwayne have in the second game? There you go, right? Now that you understand that, let's do a couple of operations. Or let's just talk about the first one, because this would be torture for us to actually do it. It wouldn't be torture. I think that's a little overstatement, but it would be boring. So let's just symbolically represent this. Find the matrix that gives the totals for the tournament in each category. What would that be symbolically using F and S? Find the matrix that gives the totals for the tournament in each category. What would that be? What operation? So symbolically, you would just say F plus S, right? And then, add entry-wise, and you'd have a single matrix giving you the totals for both games. Okay, that's not the interesting example. Here's the more interesting example. So this is a matrix multiplication. I'm saying take the matrix, the row matrix, 1, 1, 1, 1, 1, 5 ones times F. Now, before we talk about it, let's write that down. If I write down the 5 ones, 1, 2, 3, 4, 5. So we're taking this matrix of ones times F, essentially. Is the multiplication defined? What's the order of the first matrix with ones in it? It's a one row, by 5 columns, right? What's the order of F? 5 rows by 3 columns. So you see these inner numbers match. So the multiplication is defined. All right, so I want you guys to do this. And once you see how to do it, it's not going to be hard to determine what this is going to give you. Some of you may already see what this gives you if you do this multiplication. I want you guys to try this multiplication. So since there's only one row in the left-hand matrix of ones, well, and you can look at the dimensions, can you predict for me what the dimension of the outcome is going to be? The order of the resulting matrix, what's that going to be? 1 by 3. So I want you guys to do that now. Just in your notes. So you're going to get the first entry, it's a 1 by 3 matrix, so your product matrix is only going to have one row with essentially 3 entries, 3 columns, 3 entries. So to get the first entry, you're going to take the row of ones and multiply it times the first column. And then you get the second entry, multiply times the second column, third entry, third column. Won't take you very long. And keep in mind what the columns represent. Points, rebounds, and minutes played. Points, rebounds, and minutes. And I want you to, first of all, calculate this, and then tell me in a sentence what it really represents. Right? So give that a shot. So let's talk about this. Don't give me an interpretation yet. Just tell me what's the first entry going to be, and don't give me the actual number yet. What do you do to get it? Matrix multiplication wise, you would take what plus what plus what plus what? Yeah, essentially by multiplying by a row with all ones times the first column, that's just going to have the effect of adding all the entries in the first column. Did everybody see that? Yeah, so you get 21 plus 18 plus 10 plus 8 plus 15. And then you can predict, oh, if I want the second entry, I multiply by that row of ones times the second entry. Again, I'm just going to be taking 1 times 5 plus 1 times 9 plus 1 times 7 plus 1 times 3 plus 1 times 12. Okay, and then third entry, same idea. You end up adding the 35 plus the 32 plus the 28 plus the 30, and squeeze it in here, plus the 32. Everybody with me? And what do you end up with? 72. 157. Do I have confirmation? Okay. All right, well, that's all well and good if you can do the multiplication. What does it mean? What does this matrix represent? Yeah, so notice what the columns count stays the same, right? The category stays the same. And so the 72 is going to represent the total number of points scored by the starting 5 players, right? That's column 1. Column 2, 36, is the total number of rebounds by the starting 5. And then column 3, the total number of minutes played. So how would you summarize that? So the product represents the total number of points I'll say points scored, rebounds, and minutes played by the starting 5 in what? This was the F matrix, right? So the first game, in the first game. Proofread it. The product represents the total number of points scored, rebounds, and minutes played by the starting 5 in the first game. Yeah? All right, symbolically, could you tell? Oh, so by the way, let's back up. You may not care about this problem. I don't care about this problem. But what we're doing in this problem matters. The way this shows you how matrix multiplication can be used to manipulate and do statistical analysis on data, right? The data in this, again, you may not care about the particular data in this problem, and that's not the point. The point is you can analyze massive amounts of data by programming a computer to do this sort of multiplication on huge matrices. And data analysis is huge these days. You've heard of data mining, right? Well, you're being data mined as we speak, right? By big companies. And so far, it's been pretty harmless. Will it always be harmless? I don't know. It's a scary future. But it's also an exciting future, right? And there's going to be many opportunities in statistics and data analysis. So if you kind of like this or you don't mind it, you know, you get a degree in statistics pretty easily. Well, okay, not easily, but it would take a couple years, and you could be an analyst. Do you guys know what an actuary does? They work for insurance companies. Well, it can be if it's life insurance, sure. But nobody knows, I mean, who's going to get in a car accident in here in the next 5 years, right? But you can make predictions based on data analysis, how many car accidents will occur per whatever number of people. And you can use that data to see how much you should charge for insurance, right? And then you charge that amount, and the insurance company makes money, and the insured gets covered. It's a win-win, right? All right.